We have to make money from the guy. No, it's not.
Test. Test is working. Hello, Heli. Hello, Said. Hello, Hadassah. Hello, Lola. Please confirm if you hear me.
We can hear you.
Oh, okay. Yeah, thank you. I'll check if I can bring in camera. Oh, okay. Yeah. So many thanks for connecting. Let me start sharing right away. So here is the list of subjects for presentations. So as I see Haley, Lola, Said and Hanmant already filled, but everyone should do it. It's like another midterm in the class, and it would be great if you can do it on 7th, but I know that your schedules do not allow do it once, then we will sacrifice 2 meetings to make the subjects. And I believe when we will meet tomorrow in the lab, we will cover all subjects, and you will help each other to go over them. So if is anyone oh, Amir, you let me check if you are co-host and maybe make more co-hosts. Just in case if there will be more people joining. I just randomly made a couple of you co-hosts. Amir, Hadassah, Haley. Just in case if you see anyone joins, please admit right away. The meeting today will be very intense, and I just hope that you were able to watch recordings at least from yesterday, and at most everything I shared before. So we need to complete Hartree-Fock theory today to be in the schedule. So we just getting theories that allow to compute observables and compare to experiment. And here is the navigation map of what we do. I will waste a little time and repeat just in case you are not. Oh, hello, Mara. Here yesterday we're not watching recording. So the serious and complete description of Hartree-Fock theory needs about 7 lectures. We squeeze it and replace by watching, but here are the components. So everything is based on Slater determinant for antisymmetric wave function. One can get justification by considering coupled spins. Also, there is a concept of mean field where all but one electrons create background electric field that repel the last electron. There is also a concept of variational theorem that we discussed yesterday, which tells if one knows ideal wave function of the ground state, any modification will increase the energy. And then there are two contributions to multi-electron Coulombic energy, the Coulomb and exchange, which splits Coulomb on two parts, actual Coulomb and exchange. Exchange has negative stabilization part, and it is why we do not disintegrate on pieces immediately and all molecules in our universe. So exchange interaction is extremely important. All of these concepts needs to be combined into the way that can be solved on computer. So one electron Fock operator in a specific basis. And we will cover this last things today. Feel free to stop me anytime. It's better we sacrifice completeness, but we have understanding. So here are the subjects that you are voting for. Let me go once again to the, yes, so here is the link to the table. You see there are a couple of subjects already taken, but please consider to vote before tomorrow's lab so that I can confirm the schedule, and on Monday, coming Monday and Tuesday, we'll do these presentations which serve as a midterm. And it just covers what we basically did in the lab. Let's keep homework this year because you better focus on the presentations. But when we will return, when we'll go to the next chapter, we will need to build the simplest model of conjugated polymer, and we will work on it in the next chapter in the next month. So yeah, here is just a verbal summary of what we are doing and what we're trying to do. Let me just look on your faces once again and ask you for confirmation. So please raise hands or thumb up who was either attending yesterday meeting or watching it in recording. What? 1, 2, 3, 4, 5. Okay, then I will not repeat things because it's a kind of a challenging marathon to cover this material. So when we do have electron interaction, it is integral over 2 points in space and includes 4 wave functions. So it is, if we do it in indices, it is object with 2 indices. And if you want to work in the limit of 1 electron quantum mechanics, we need operator that matrix that has 2 indices. Therefore, we do integration over positions of the second electron, and out of multi-electronic Coulomb interaction, we fabricate effective 1 electron Coulomb operator, and it is represented as a black box and corresponds to the electron like repelling from a wall, and wall means all other electrons that repel it. The exchange in the same language means that the electron in number 1 disappears from state from orbital 1 and reappears in the orbital 2 upon hitting the wall. So it's a little unnatural, and sign of this process is negative, which makes stabilization. So the 1 electron Fock operator includes kinetic energy of one electron attraction of this electron number 1 to all nuclei, and then the positive Coulomb and negative exchange of our favorite electron number 1 to all but one, the rest of electrons. Hartree-Fock theory is here, but it is very not practical. We can just solve Schrödinger or Fock equation, which looks like Schrödinger equation for an electron, then practice Slater determinant, and in some sense it will be done, but it is very non-doable for programmers, and we need to do a trick. Specifically, we need to go into a basis, and at least a half of our meeting will be about the basis. So the equation here looks like Schrödinger equation. So the one electron Fock operator, unknown molecular orbital, energy of molecular orbital. Right? And the original development was done by Hartree. He didn't include antisymmetry, but he did the rest of things. And the Fock has contributed the idea that one needs to bring this antisymmetry and exchange. Positive and negative. And just a little reminder, although you confirmed that you were yesterday, the molecular orbitals, one electron molecular orbitals, are represented as superposition of atomic orbitals, like SPD atomic orbitals localized on different ions. And this C are expansion coefficients. So we need to formulate an algorithm, set of equations, and algorithm that will help us to find this expansion coefficient C. So here is a little overview of the concept of basis functions. The one of you who will review basis functions in the presentations next week is expected to do a little bit more than I'm doing right now, and a little bit better. So I'm just giving a brief overview. The S orbital, if you have only one dimension, it looks like a cusp, like e to the minus distance, absolute value difference, energy distance difference between position of ion and position of electron. So the closer the electron to the atom, the higher the probability if you take it absolute value square. So it's chi 2. If we are on the second ion, it will be just subtracting from another one. If it is pi orbital, then this exponential is multiplied by distance of the electron from the ion, and it gives this nodal things. There is a trick. If one replaces this e to the power minus absolute value of distance into e to the power minus distance squared, it is wrong mathematically, but one can carefully do it by adjusting coefficients and identify that on the main part of the function which defines chemistry, these functions are not very far from each other. Of course, they are different in the absolute vicinity of the ion, and they're different as we go to the infinity. But this is acceptable error. So replacing atomic orbitals with Gaussian type orbitals, G, T, O, is the main reason why the software we are using right now is referred to as Gaussian. Make sense? We are finishing Gaussian this week and on your presentations. We will soon start new software which uses very different basis set, very different concept. And instead of orbitals localized on atoms, it will use delocalized plane waves that are looks like oscillations across the whole space or across the whole unit cell. Those are most applicable to nanostructures, nanotubes, thin films, and it is very much used in engineering. Okay. So what I am going to do right now, although the time is limited, we should do things carefully. By now, I do accept that we use only atomic basis, because historically it was how theories were developed. Now, I assume that molecular orbitals are composed as a superposition of atomic orbitals. And I'm going to assume that, not assume, agree that all atomic orbitals on the same ion are orthogonal. And if they are on the different ions, there will be some additional trick. But if you are a big supporter of quantum theory, if you went through this class or had some exposure, you may have heard the idea of expanding functions over the basis and then removing, making a transition from continuous functions to vectors, to expansion coefficients, by applying orthogonality relation. So it is what I am going to practice right now. I want to do such mathematical tricks which will keep these same ideas, these same interactions, but I'm going to remove atomic functions from my explicit consideration because they are already given to us. We are not going to modify them, but we need to modify expansion coefficients. And once again, although you confirmed you've heard yesterday meeting, here is a very brief summary of what we are doing. A goal of any electronic structure theory is to get total energy of the system, many electron system. Total energy can be obtained as a matrix element of Hamiltonian in Bra and Ket of the many electron wave function. And the many electron wave function is a Slater determinant. And the Slater determinant is like subtractions of products of one electronic molecular orbitals. So in order to find the total energy, we need to have molecular orbitals. Make sense? Okay. And we are going to use one electronic Fock operator that inherits multi-electronic effects and makes such molecular orbitals that carry on information about electron-electron interaction in the right way. Okay, and so it already sounds like a lot. And in order to make it efficient, I'm going to focus on expansion coefficients rather than continuous functions. Okay, so if I try to practice orthogonality relations, the atomic orbitals chi are orthogonal. Let me highlight it. If they are located on the same ion. So P, S, P, D orbitals on the same atom, on the same ion, are orthogonal. But if you have like P orbital on ion number 1 and S orbital on the ion number 2, they are neither equal nor their overlap will be not a delta function. There will be something in between. And therefore, we just need to admit this fact and introduce this concept of overlap matrix element. So it is situation when atomic orbitals localized on different ions are not orthogonal, but they have some value between 0 and 1 when you overlap them. Make sense? Okay. Other than that, it will be relatively standard way to remove orbitals. And here is just notation for this 2 points and 4 orbitals by putting different values of making these indices equal in a pairwise fashion. One can make this integral into either Coulomb or exchange. It's just what people are using in the literature. Okay, so one electron Fock operator. We are going to plug in expansion of a molecular orbital in terms of AO, atomic orbitals. So it will be main part of what we do today. I do have slides which are much less ugly, which are typed in the right way, but the idea is the same. So the black part, F, here is our Fock operator. The red part is our unknown function, and energy is eigenenergy. So mathematically, it is not forbidden to multiply both left and right part of the equation by the same factor or apply the same operation. So we bring in this pink part. So we multiply left and right part by the atomic orbital with index mu, and we integrate over electron position R1. So we hope that through orthogonality or something similar to orthogonality, we will exclude orbitals from explicit consideration, and we will have only expansion coefficients and matrix elements. So in the bottom line, the yellow highlight are matrix elements, and not highlighted things are expansion coefficients. Please confirm if general direction of thought is okay. Okay, yeah, I'll go forward. Okay. So plugging in expansion coefficients, multiplying by the independent atomic orbital and performing integration. So when we use an idea on the right part that atomic orbitals are not necessarily orthogonal, we just use this S sub mu n instead of delta function, and we just call it overlap integral. So it is a term in the literature. Okay. And what is left? Yeah, I think I'm repeating the same thing. And what is left? This yellow highlight on the right part, it is bra and ket of this newly contributed and old atomic orbital. So we can replace this integral by bra and ket notation of one electron Fock operator. So if you take matrix elements with certain indices, so instead of orbital, we will have the matrix. And then we are getting the matrix with 2 indices and the expansion coefficient with 1 active index over, so this index nu goes over atomic orbitals. And the same structure appears on the right side. we will have this S matrix with two indices and C expansion coefficient with one active index nu. You can say that there is a second index I, but this index I is just a number of eigenstate. We are not involved into summation. So we will just find several eigenstates and several eigenenergies. So what we are what we are getting is shown here in the simplified form. So, of course, there are no real problems where two expansion coefficients are enough for real molecules. I'm just showing it as an example. But it is just an illustration how the Fock matrix and expansion coefficients are dealing together. So we are getting eigenvalue problem in the as one does in linear algebra in matrix form, right? I think, and this idea to reformulate Hartree-Fock equation in this matrix form came from Clemens Ruthan, who claims that he got this idea while listening to the Chicago Symphony. Okay. So, okay, it was a couple of garbage slides where I repeated the same idea, but here we are getting to the practical side. The set of expansion coefficients for, let's say, eigenstate number one, here the numbers go over all atomic orbitals and all ions, and we can save it as a vector. So in the same way, we can formulate the matrix elements of the Fock operator in the form of a matrix. And overlap matrix also is like object with two indices. So in these notations, we are getting the eigenvalue problem. This eigenvalue problem provides us with expansion coefficients of molecular orbitals and energies of molecular orbitals that you did observe while running Hartree-Fock calculations, right? So the little difference from typical eigenvalue problems that we have seen in other circumstances is this overlap matrix. But mathematically, no one forbids us to subtract left and right part, which means we just, instead of delta function, we just subtract the overlap matrix, and it still remains the eigenvalue problem. So one can formulate it as Fock matrix minus unknown eigenvalue times overlap matrix multiplied by a vector of unknown coefficients equals 0. And it is called Ruthan equation. So if one is trying to solve, one process it in a standard way by finding, well, no one does it by pen and paper. Maybe there are a couple of exercises in advanced courses when one makes this matrix, but basically there are characteristic equations when matrix eigenvalue problem is converted into polynomial equation, and these eigenvalues are found, right? So here is an idea how this equation is integrated into the whole procedure, because we do need to find so orbitals and their energies are interesting and useful, but they are just auxiliary concepts. They just help to go through. And the main goal is total energy and multi-electron wave function. So originally one starts from coordinates, makes a random guess of molecular orbitals, and then one does formulate the Fock matrix. And when Fock matrix is diagonalized, one is getting into the loop, because the shape of molecular orbitals, the expansion coefficients, indirectly affect the degree how strong or how weak Coulomb and exchange are for this molecule. And the idea is that if one uses output of one single diagonalization, so after diagonalization, one plugs in molecular orbital set into Slater determinant, finds total energy, and repeats the cycle. So there is an idea, if one repeats the cycle and again and uses output of one cycle as an input to another one, the total energy of the molecule becomes more and more precise. It will approach closer and closer to ideal ground state. And the background for this procedure is variational theorem. So the total energy of the molecule can be considered as the summation of energies of all occupied orbitals, plus this pairwise contribution from Coulomb and exchange matrix elements. Here is a technical detail that it's not main goal for us to deal with it in our derivations, but it's better to be aware how things are going. So these equations show how the Fock matrix includes the expansion coefficients of molecular orbitals. So depending this index P in a blue box is referred to as density matrix, and it is not density matrix that is typically introduced in quantum mechanics. It's a specific density matrix for Hartree-Fock, and it includes the product, pairwise product of expansion coefficients with a summation of all occupied molecular orbitals. So it projects expansion coefficients into this two index object, which refers to atomic orbitals. And here, if we make summation, if you convolute this density matrix with Coulomb and exchange parts between for each like combination of atomic orbitals, this will give the value of a Fock matrix for the next step. So if some of us will try to read either textbooks or manual for Gaussian software where they try to summarize Hartree-Fock in like half a page, this equation will necessarily be there. So it is a practical part of implementing Hartree-Fock. Okay. And here is a little quiz that we can review here, but I'm asking everyone, especially those who are not in the class, to fill it and email me. It will take like maybe a few minutes. Just I'll show all steps, but it's better if you try to do it yourself and maybe add comments. So in this, I'll add another comment. So why it is needed, why we do such flowchart, what is the benefit for us as researchers, like applied researchers, and what is the connection with the previous and next chapters in the course? When we were speaking about geometry optimization, we were varying interatomic distances, positions of ions. According to variation of interatomic positions, we were browsing on the potential energy surface, making this steepest descent or some other algorithm, and approaching closer and closer to minimum of the potential energy, right? Here, and it was summarized in the flow chart, how we do next and next step and approach closer to the minimum. Here, we are doing absolutely the same. The only difference between geometry optimization and Hartree-Fock is that in geometry optimization, our coordinates were real Cartesian coordinates of ions, right? And in Hartree-Fock, our coordinates are expansion coefficients of molecular orbitals over atomic orbitals. So we vary expansion coefficients of molecular orbitals until we are getting to the minimum of the total energy. Make sense? Please confirm if it is like, okay, you're absolutely against or more or less. Okay, 45 degrees. Yeah, thank you, Hadassah. So how can we feel it? So Fock matrix, new expansion coefficients, they are going into total energy. And somewhere in this loop, there should be, yeah, maybe here, that density matrix equation, this P sigma lambda, is used to make new Fock orbital, Fock operator, and Fock matrix. And then we repeat it in cycle, and this little diamond tells how the total energy on new iteration relates to total energy on the previous iteration. If it is smaller than tolerance limit, then we can say we have finished this calculation. Yeah, it's just several attempts. And in the file that I did send to everyone, one can try to play this, to fill this table just by moving the most important equations in the right way to arrange the correct formulation of the algorithm that is later implemented in the computer code. So basically, by following this little flowchart and minimalistic level of programming, one can redo Hartree-Fock code without and save money on buying software. Okay, and we do not need it to do it, but we need to have general idea what is going on. So I encourage you to practice this little redistribution of boxes of like equations over boxes and make comments as you interpret it. Okay, so by now I want to congratulate you that you've got the main component of Hartree-Fock theory. But if you remember the first slide that I'm trying to show at each lecture, you remember there is a like Schrödinger equation, atomic positions, software and hardware, given observables, and then compared to experiment, right? So the goal, in some sense, computational chemistry and material science replaces experimental instruments to characterize materials. And how do we connect our assumingly correct Hartree-Fock calculations to the properties of real molecules and real materials? Which observables can we extract, can we predict and interpret? So I need to rush through, but maybe just a little interview. Haley, which observables would you like to predict with Hartree-Fock?
Momentum.
Momentum of whom? Or of what?
A particle. An electron.
Which particle?
An electron.
But if we have a molecule like your metal organic complex with thiophene tail, electron stays in eigenstate. It doesn't move across the molecule. It just stays in eigenstate. So momentum is doubtful. What else can we extract from Hartree-Fock? Or from any electronic structure? If anyone wants to give an idea, do not hesitate. I want it to be only a positive experience. Like, hey, what do you extract when you do electronic structure calculations? What do you extract from your data? What do you report to your colleagues or to your advisor about certain molecule?
Energy.
Energy of what?
The molecule.
Total energy of molecule. And was your advisor curious about band gap energy?
Yes.
Okay, band gap energy, right? So difference between ground and excited.
Yes.
Okay, that's very good. Yeah, thank you. Do we have chemists who appreciate electrochemistry, reduction and oxidation potentials? Just raise hands if this word tells something to you. Electrochemistry, redox potential. I think I wanted to remove my focus from Haley, but I think you are the most chemical chemist in the audience. So come on, no, the rest of us were doing either engineering or physics. So okay, I'll just tell myself, when the molecule is characterized, it is important if it is easy or hard to remove an electron from there, right? Removing an electron from molecule is oxidation, right? Please correct me if I'm wrong. And some molecules give up their electrons really easy. So they are electron donating molecules or electron donating groups. And some molecules or groups are very greedy. They do not, no, I do not give you my electron. So it means they have different ionization energy. The energy needed to remove an electron is different. And for true chemical chemists, it is important because they, based on this value, they can predict whether a pair of molecules will exchange an electron. Like if you have one molecule that really easily gives up electron, another that really wants to take this electron, they probably will form a bond. Make sense? And another, if just connected to it, if a molecule wants to accept electron, it is called electron affinity. So this this is one of the simplest and chemically relevant observables. Of course, there are others. Total energy just tells whether your molecule will be stable, or if the total energy is bigger than 0, it means it will decompose. Even if you compute properties of a molecule and found that total energy is positive, it's highly likely that it doesn't exist in nature. So as soon as you synthesize it, it will explode. And if the energy is really low, it means the molecule has right to live. It will be stable. So I'm going to make a brief introduction to these things in the remaining 15 minutes. And it is much simpler compared to what we were doing previous hour and previous days. But for practical applied research, it is much more important. So it is kind of a way for real applied research, publications, discussion with colleagues, and these same observables can be computed by other methods which are superior compared to Hartree-Fock. So Hartree-Fock is important intellectually, but practically it doesn't give competitive results by today because there are much better methods. Okay, and there is one more thing that can be criticized, but I want to give it today, and I hope I will be able to. Some of the researchers are very curious about optical signatures, so-called spectra, UV visible spectra. The minimalistic level to get reliable spectra is so-called TD-DFT that we hopefully cover in April. But some very much approximate spectra can be extracted from Hartree-Fock or from DFT. And I just want to give a general idea, very basic idea, only for as a basis for our future consideration, how the computational results on Hartree-Fock theory can help us to check if the molecule is able to interact with light. So light to matter interaction. Okay, is it enough for motivation? Okay, I will hide your faces, but if you if there are questions, just start talking. I'll immediately go back to discussion mode. Okay, so most typical way to probe properties of materials in the instruments is to irradiate it by electromagnetic radiation, which can be of radio frequency for nuclear magnetic resonance or visible for UVVs and some other ranges. So electromagnetic radiation means there are waves coupled electric and magnetic field which change both in space and time, which is shown here by this exponential function. So E capital is electric field, and there are like phase, frequency. The individual charge will be pulled up and down by electric field, but most molecules are neutral. So the total charge of a molecule which is not ionized is 0. But typically there are ranges of molecules which have higher or lower concentration of charge, and there is a dipole between them, right? So if a molecule is polar, if it has a dipole, then electric field will reorient it, right? So electric field vector times vector of dipole gives energy of light to matter interaction or field to dipole interaction. And if the field is oscillating, it is the same story. So the little thing on the bottom here is like we have Hamiltonian or Fock operator H naught, which is in absence of electric field, minus dipole times electric field in presence of electric field. So if you want to be meticulous, the dipole is all positive minus all negative. So positive are positions of ions times charge of the ion. Negative are average position of electrons, or positions of all electrons. You see that this operator is substantially multi-electronic. It includes summation over all electrons. It's not an easy thing. Now, what I'm going to model in the remaining 10 minutes, or model in an abstract hypothetical way. Suppose we do have a hypothetical molecule that has 3 orbitals, no spins, and only 2 electrons. And we are considering that orbital number 1 is filled, orbital number 2 is filled, orbital number 3 is empty. We apply electromagnetic radiation of the frequency h bar capital omega and promote from orbital 2 to orbital 3. So the probability of such transition that Amos from physical chemistry class would like to insert into Fermi's golden rule will be a matrix element of interaction. So one would need to interaction between light and matter instead of this operator O. And the initial and final are Slater determinants of the multi-electron wave function before and after interaction. So Slater orbital of initial will be ground state Slater determinant. The final will be Slater determinant of the system when population went up to the orbital number 3. Right? Okay. So I am going to process this little artificial experiment in the simplest way. So we have 2 electrons. I do remove positive charges because they are constant, and put the mu operator simply as a summation of position of first electron and position of second. Slater determinant of the ground state depends on first and second wave function electron. I also, instead of Slater, I do just Hartree product. But if I carefully do real Slater determinant, the result will be the same. Just want to save time. So electron number 1 in orbital number 1, electron number 2 in orbital number 2. If I need excited state, then electron number 1 in orbital number 1, electron number 2 in orbital number 3. So I do have these 2 multi-electronic wave functions, and I want to find the matrix element of light to matter interaction or transition dipole, because electric field also is a constant, in between, in Bryan-Cat of this multi-electronic wave functions. So for excited, I will use our excited wave function. For ground, I will use our ground wave function. And the protocol of finding expectation value of this Bryan-Cat means just integrating over position of electron 1 and position electron 2. Same things can be done with infinite number of electrons, but it will be just more writing. So once again, ground, excited, operator in between, and here is what I'm going to do. So matrix element of going from ground to excited. Bra-Cat operator. 6 minutes left. let me just double check your confirmation. Is it okay by now? More or less, okay. Hiding. So on the bottom, we see that operator has two terms. So if you will open brackets, there will be like two integrals, one with everything on the left, R1, everything on the right. Second, everything on the left, R2, everything on the right. And then I do want to process these two integrals using the property of orthogonality, that good orbitals are orthogonal to each other. So bra R1 ket, bra R2 ket. So what do we observe here? It's an interesting thing. In the first integral, which includes R1, when we perform integration over the first electron, position of the first electron, dr1, we have orbital electron 1 in the conjugated of orbital 1 on the left, and we have orbital 1 in the non-conjugated orbital 1 on the right. So the things that are underlined by red, and the R1, which will be combined with them. Now the another portion which is independent is integration of dr2, phi 2, phi 3 of R2. So what is really cool and important? It's maybe the only little step that is non-trivial and needs thinking rather than rewriting the same equation. There are different orbitals, phi 2 and phi 3, depending on the same variable. So if you perform integration over dr2, then this and this will work as orthogonality. Because orbitals 2 and 3 are orthogonal, the integration of over R2 will give us 0 no matter of the other factors. So we can prove that the first part will be 0. And I'm going to show it once again in the next slides. And if I do integration over the second part, it will be non-zero. It will be something different. So instead of 2 terms, we'll have only 1. And this is extremely interesting and important because in this way, we will convert multi-electron expectation value, multi-electron matrix element into single electron matrix element, which is way much simpler than anything related to multi-electron things. So there is a way to extract properties of multi-electronic systems from single electron matrix elements. I'm going to show a few more slides and repeat this idea once again. So the second part, which is non-zero, can be factorized as the integral over R1, which will have phi 1 R1, phi 1 R1, which will be 1 due to orthogonality. And the second part, integral over R2, phi 2 R2, R2, and phi 3 R2. So instead of multi-electronic matrix element, we will have only the lower line, which will have the single electron dipole matrix element. So it will show matrix element of the position operator for transition between orbital 2 and orbital 3. Does it make sense? Please confirm or do not confirm or show that it's not enough arguments. Okay. Thank you for your report. I'll go into next. Oh, I believe I'm repeating the same idea in again and again in a couple of. Let me find the slide that is typed instead of handwritten. Yes. Okay. So this should be better. So here we have the whole expression. Matrix element of R1 plus R2 in the bra and ket of ground and excited state. So there are two terms which are separated by plus sign, and there are in each term there are two factors. One factor is integration over R1, second factor integration over R2. In the second term, integration over R1, integration over R2. So in both groups, we have a factor that contains position operator between orbitals in red, and we have a factor that does not have position between orbitals, right? So the factor that does not have position between orbitals may have the same indices of orbitals or different indices of orbitals. So if indices are the same, this factor is replaced by 1 and removed. If indices are different, this factor is replaced by 0 and removed together with the second factor. So there is a good orbitals that are obtained by diagonalization must obey orthonormal property. If one multiply them by each other and integrates, we will get either 0 or 1. 1 if the indices are the same, 0 if indices are different. It's just general property of any solutions of eigenvalue problem. And due to these tricks, in these 4 lines, result will inherit only the bottom line. So originally, we started from a matrix element of multi-electronic system. And here we have only single electron, electron number 2, and 2 orbitals. Absolutely the same derivation can be made for 3, 5, 10, 100,000 electrons. So if you look optical transitions in multi-electron system, it is determined just by matrix element of transition between 2 1-electron orbitals. And it is a beautiful result. It makes our life so simple if we need to predict optical properties of materials. Why we need transition dipole matrix element? Because it gives us intensity of transitions. It, if you do in spectroscopy, the peaks, the height of the peaks in spectra are proportional to transition dipole matrix element squared. Okay, so it tells whether your transition is bright or dark. And here is the summary of the same thing in just shorthand notation. Please raise hands if you need to leave immediately. If anyone needs to leave immediately, please raise hands if you give me a couple of minutes to finish the thought. Okay, thank you. But if your schedule doesn't allow, feel free to depart. I realize and understand that we are recorded. Okay. Oh, okay. The thought is finished. Oh, no, I'll continue. I'll skip the slides. They are introduction for next chapter for solid states, which I'll better skip and show in the other thing. But here is something I want to tell about electron affinity and the ionization energy. So we all agree the total energy is composed of the energies of occupied orbitals and these pairwise contributions from Coulomb exchange. But there was a researcher, Dr. Koopman, who told, what if we completely neglect this term? It will be, the numbers will be not precise, but maybe we can get important insights into the science, into the properties of molecules. So just what if we temporarily neglect this multi-electronic properties? If this Koopman approach is correct, then total number of total energy of the system is just summation of orbital energies of those orbitals which are occupied, right? So it is not absolutely correct. It's just a way to qualitatively analyze this. And here I'm going to show an image that was shown on the presentations similar that you are going to do next week by Christian Newis, who was undergraduate while taking this course. So we have occupied orbitals, right? And if we remove one electron from highest occupied, then it will be exactly the energy that we need to ionize the system. So it will be basically energy of HOMO is equal to ionization energy. If we bring in one more electron, so it's LUMO, it will be the energy needed to put there an electron affinity. So just by looking, if we believe Koopman's hypothesis, and if we know the energies of HOMO and LUMO, we can tell ionization energy, ionization potential, ionization affinity, and the band gap. Here is a little proof of this, and it will be the last thing. So a little proof of this. So I consider three situations: neutral molecule in the middle, molecule which we ionize by removing one electron on the left, and positive, like here is cation and here is anion, where I add one more electron. So I'm going to just write down Koopman's equation for each of them and compare total energy of neutral, anion, and cation with one less and one more electrons. So here it is, and I hope very much it will be the very last thing. So total energy is summation of all occupied. I look in the middle. Neutral system, E1, E2, blah blah blah, time until E number n, or n number of electrons. Now, if I remove one electron, it will be from 1 to n minus 1. So the difference between these two energies, between total energy of the system with all electrons and all but one, will be just equal. So if you subtract, red gives cancellation, and only energy of HOMO will contribute to ionization energy. So it's a little proof that HOMO, energy of HOMO orbital, gives us ionization energy. So it's a red line here, En minus 1 minus En. If we add an electron, we have one more contribution, E sub n plus 1. And if we make a subtraction of the anion, E of n plus 1, and neutral, E sub n, we will have that E capital. Then the electron affinity will be just equal to energy of orbital number n plus 1, which means energy of LUMO. Okay? So, and this, what we briefly went over, it's not like immediately spectra and immediate papers coming out of calculations, but it is a way how predict some properties of molecules, of real molecules, that can be compared to real life. And I would call this section of our today's lecture observables. So we considered observables. Okay. I did skip introduction to periodic solid states, but we are already over time. So meeting is done. Thank you very much for your interest and contribution. Looking forward to see you tomorrow at the lab. And by beginning of the tomorrow lab, I hope to have the votes on what you want to present next week. So if you are not sure, you can select 2 subjects and I will mitigate the conflicts. Okay, meeting is done. Everyone is welcome to disconnect, and I'll stay here just in case if there are extra questions. Well, do you have any questions?